Today we're going to look at graphs of linear functions, and then once we know how to graph linear functions, we'll talk about how to write equations of functions given certain characteristics of them. So first we're going to talk about how we can graph vertical and horizontal lines, which have very distinct equation types. I actually won't spend too much time on that one. The video did a good job of explaining. For vertical lines, we'll just make a note of it at the top here. For vertical lines, the equation will always look like x equals a. Let's not even put a. We'll say x equals a number. That's going to be the equation of a vertical line that passes through that number on the x-axis. So x equals -3, for example, on this example here, will be a vertical line that passes through -3 on the x-axis. So you find -3 on the x-axis, and then you have a vertical line that passes through that line, or through that point, excuse me. All right, so this is x equals -3, and you can do this by doing an xy table where x is forced to be -3 because of the equation. So no matter what the y is, when y is -3, x is -3. When y is -2, x is -2, and so on. So no matter, whatever y is, x is always going to be -3. Sorry, I got carried away there. When y is 2, x is still -3. So x is -3 no matter what value y is. So then you get all of these points where the x value is -3. So it's -3 comma something every single point. So then you get a vertical line. As far as a horizontal line goes, if a vertical line is x equals a number, then a horizontal line will be y equals a number. And a horizontal line is going to go left to right. It's going to cross the y-axis wherever this number indicates. So if we look at the next example on the page, y equals 4. We go to 4 on the y-axis, put a point, and then we have a horizontal line that passes through that point. This is y equals 4. And if you were to do an xy table for this and plot points, no matter what x you plug in, -2, -1, 0, 1, 2, y value is always going to be 4 because there is no place to plug in an x value. The y value is 4. Y equals 4 just means regardless of what x is, y is 4. Okay, so you have -2, 4, -1, 4, 0, 4, and so on. That's all of these points in this horizontal line. As far as slope is concerned, because remember we know how to find slope from a line, the slope of a vertical line is undefined, and the slope of a horizontal line is 0. Just something to keep in mind when we talk about vertical lines. There is no slope, it's undefined, and then slope is equal to 0 for a horizontal line. And all of that is kind of just summarized in this box here, so if you want to put a bookmark on this, this is where all of that information is. Right? It gives you the equation of a vertical and horizontal line. It tells you the slope of vertical and horizontal lines. So just keep those in mind. Okay, next we're going to talk about how to determine whether graphs of lines are parallel, perpendicular, or neither. But first, before we do that, let's go over how to find slope. how do we find slope of a line? Slope, which is m, equals what? How do we find the slope of a line? There's a few different phrases.
Rise over run?
Yeah, there's a few different things that we've talked, that we know about slope. Rise over run is one of them. How else can we, or how can we actually compute that if we have points on the line?
y2 minus y1 over x2 minus x1.
Good. So it's the change in the y points, or the y values, which is the rise, over the change in the x values, which is the run. So when we talk about rise, we're talking about we take 2 points on the line, like this point and this point, for example, and we look at how far up we go. That's the rise. That's the y2 minus y1. And then we measure how far to the right we go. That's the run. That's x2 minus x1. And if your rise is actually going up and going to the right, then you have a positive slope. But in this case, for example, if I take this point and this point, then my rise is actually going down, right? Rise just means up or down, and then run means to the right. So if we go down and then we run to the right from one point to another, then we're going to have a negative run, or a negative slope, because we have a negative rise, right? y2 minus y1 will end up being a negative number. x2 minus x1 will always be a positive number because we're running to the right. So if you rise up and then run to the right, that's a positive slope. If you go down and then to the right, that's a negative slope. So we can compute the we can compute the slopes of these lines to kind of see the characteristics of parallel, perpendicular, neither in these three examples here. The first set of lines have a perpendicular characteristic, meaning they intersect in a 90-degree angle. So these are perpendicular. And we'll see what the slopes are for that kind of intersection. And then these are parallel. And these are neither. Just as a precursor, because this question is not asking for that. It's just asking us to find slopes. So because I know this is perpendicular, parallel, and neither, we're going to be able to look at these slopes and kind of determine what kinds of things make lines perpendicular, make lines parallel, or neither. And just looking at the slope is going to be enough to determine whether two lines are perpendicular, parallel, or neither. If we take 2 points on this orange line here, such as that one, we see that the rise, when rise is 1, the run is 2. So then the slope of the orange line, m, as rise over run, is going to be up 1 and then over 2. So the rise is 1 while the run is 2. So we see a slope of 1/2. Whereas the blue line, if I find 2 points on here, I'm going to go down 2 and over 1, meaning my blue slope as rise over run will be, since I went down 2, it'll be -2, and I went to the right one, so that's a run of 1. So we get -2 over 1, which is -2. And these two slopes, we're going to label these as opposite reciprocal. And if you read this parenthesis up here, or I'm sure the video also explained, that specifically if we have slopes that are opposite reciprocals, we're going to have perpendicular lines. So what makes these opposite reciprocal? Well, the word opposite describes that one is positive while the other one is negative, right? That's what opposite means. They're on opposite sides of the number line. And reciprocal means that the fraction is flipped, right? So if I start with 1/2 and I want to find its opposite reciprocal, we're going to flip this fraction so that it becomes 2 over 1. And then we're going to make it negative because of the opposite. So you see how these are opposite reciprocals of each other. Any questions on the opposite reciprocal perpendicular idea? Let's look at parallel lines here. Parallel lines, in order to be parallel, to never intersect, are going to have the same slope, because for them to never intersect, they need to rise and run the same amount so that they're always moving at the same kind of angle and they're never intersecting, right? So if we do the slope of the red line, rise over run, we see that we're going up 2 and over 1. And as for the green line, we see that rise over run. Again, we're going up 2 and over 1, right? That's the only way lines won't intersect, is if they're rising and running the same amount, which means their slopes will be the same. So we have same slopes for parallel lines. And then for neither, it's just going to be anything else. Anything that's not the same slopes and not exactly the opposite reciprocal. Those are the very specific situations where we have parallel and perpendicular lines. So neither, if we look at the slopes of these lines, this one we can do like a down 2 over 1, and then this one we can say goes up 2 over 1. Those seem like they're very similar to each other, but the blue slope is again rise over run will be down 2, which is negative 2 over 1, which is negative 2. And then the green line slope, rise over run, is up 2 over 1, so that's just 2. And the question we ask is, are these opposite reciprocals? And the answer is no, they're just opposites, right? One is negative 2, one is positive 2. So we don't have that reciprocal relationship. And then we also ask, are these exactly the same? And they're not, because one is negative 2 and the other one's positive 2. So then this brings us into the realm of neither. These lines are neither perfectly perpendicular, where they intersect in a 90-degree angle, nor are they parallel, where they never intersect, right? These just intersect at some other angle, but they do intersect. Right, so 3 things can happen when 2 lines are drawn. They could be perpendicular, they could be parallel, or they could just intersect at some random angle. So these 2 boxes kind of summarize everything we just talked about. Perpendicular lines form a right angle. So they form a right angle, and their slopes are opposite reciprocals of each other, meaning M1 is the reciprocal, the flipped version and negative of M2. And then there's a little extra bullet point here talking about vertical line and horizontal line. Because we talked about earlier the vertical line having an undefined slope, we can't really talk about opposite reciprocals when one of the slopes is undefined and one of the slopes is 0. But we do want to add that vertical and horizontal, a vertical and a horizontal line will always be perpendicular as well. That's kind of like an edge case where we can't really talk about perpendicular in terms of slopes, but instead we just talk about a vertical and a horizontal are always perpendicular, just because of the definition of what vertical and horizontal are. Right, so that's perpendicular lines. Parallel lines, as this box says, do not intersect, so they go in the same direction forever, and they will have the same slope and different y-intercepts. The second part is having different y-intercept is crucial for parallel lines, because if they don't have different y-intercepts, if they have the same slope and the same y-intercept, what 2 lines are we looking at if 2 lines have the same slope and the same y-intercept? what would that look like on a graph? If two equations had this, or if two lines had the same slope and the same y-intercept, what would that mean?
That they'd be directly on top of each other.
Yeah, and then we couldn't call them parallel anymore, right? Because they're actually intersecting. So parallel means lines that don't intersect. So if I have two lines that are on top of each other with the same slope and y-intercept, then we have a lot of intersections. They intersect infinitely many times. We talked about when we were solving systems of equations, right? If they're on top of each other, there's infinitely many solutions. They intersect infinitely many times, so they wouldn't be considered parallel, because parallel specifically means that lines don't intersect. And then, so slopes are equal to each other. On this one, slopes are negative reciprocals of each other. Real quick question, do we know how to find the slope of an equation given like this? Find the slope of a line given as an equation?
You would isolate y, right?
Why?
Because slope equation is supposed to be y equals mx plus b.
Good. So let me write that down on the side over here. You need to get to y equals mx plus b in the ones that aren't already in that form. And then the m is the slope. Right, so if the question is asking you to use the slopes to determine if the lines are parallel, perpendicular, or neither, we need to find the slope of the first line, we need to find the slope of the second line, and then characterize them, whether or not they're opposite reciprocals of each other, or if they're the same slope, or if it's neither of those things, right? That's what parallel, perpendicular, or neither means. So if I do one of these problems, I'll do part D. This one, I already know has a slope that's 2, right? Because that's the y equals mx plus b. That's already in the right form. And then if I were to solve this second equation for y, we're going to add 6x to both sides. 3y will equal 6x minus 9. And then divide both sides by 3. Y will equal 2x minus 3, right? And then we see that the slope of this one is also 2, right? So then the two lines have the same slope. This one has a slope of 2, this one has a slope of 2. So my answer for this one is parallel. Right, so if they have the same slope, we get parallel. If they have opposite reciprocal slopes, we get perpendicular, or we get neither, if it's none of those things. Right. Now let's talk about how to write the equation of a line parallel, perpendicular to the given line. We have two ways of writing equations of lines, right? We've talked about two different forms of an equation of a line. We've talked about the y equals mx plus b, the one we just referred to in the last problem. What was the other form? This was called the slope-intercept form. But a lot of times, even though we have the slope, we usually don't have the intercept. But instead we just have a random point. So what was the other form of a line that we covered earlier in the chapter? What was the other form called, and what did it look like?
Is it point slope form?
It is point slope form. What did it look like? Do you remember?
always forget the word. Is it y2 minus y1?
It's just y minus y1.
Okay.
And
And then
then
equals m parentheses x minus 1 or x minus x1.
good. That one is called the point slope form. And that one is the one that we're going to use more often in general, just because having the y-intercept is kind of a rare thing. So generally we're not going to have a y-intercept, but we are going to have some kind of point, and then we'll figure the slope out from the given information. So I'm going to go over this example here. Well, actually, no. I'm going to get you started on this example here, because it is the last example, so I want you to work on some of it. We're given a line, so that's our given information. We have a line to begin with. First question to find this says to find the slope of the line L. I think you guys can do that part. You just put this in y equals mx plus p form, and then you pick out the m that is your slope, right? So this just means find m. And then once you find the slope, we can do a few things with that slope. For example, part B says find a equation of the line containing the point 1 comma 4 that is parallel to L. This is asking you to find the equation of a new line. So this is line L. We're writing the equation of a new line that's parallel to the old line L and passes through the point 1 comma 4. So we're given a point here, and then from part A, we know that the slope of L is going to be something. And if we want a line that's parallel to L, what do we need to use for the slope of the new line? So slope of new line. What do we need the slopes to be if we're going to write a new line that's parallel to L?
It needs the same slope
It
as
needs-
line L.
Good. Slope of new line should be same as L. Right, so that's just a little note for you to how to do that problem. So the new line is going to have the same slope as L, but it's now going to go through this point, which I don't think L would have gone through this point, otherwise this problem wouldn't make sense. So this is a point that L doesn't go through, but if we're given a point to go through and we know the slope is going to be the same as L, then we can use our point slope form to write the equation of that new line. Okay, so since we have a point, we have the point and we have the slope, we're going to use point slope form to write new equation, or to write equation of new line. Right, so that'll be kind of the steps, because we found the point, or we found the slope, and then we're given a point. Because it's parallel, we just use that same slope from part A, and then we use this new point to write the equation of the line. Okay, and then part C is very similar, right? It says find the equation of a line, so a new line again containing the point 1 comma 4. It's the same point as part B. So the difference in part C is that we want the new line to be perpendicular to L. So if we want the new line to be perpendicular to L, the slope of the new line should be opposite reciprocal of L. Right, so whatever slope we found in part A, we find the opposite reciprocal of that, and that's the slope we're going to use for part C, because it says perpendicular. And then the point is the same. To write the equation, again, you would use the point slope form, so that part is the same for this question. Once you have your new slope and your point, then you can write the equation using point slope form. And then once you have all three equations, you'll have this equation, you'll have another equation here, you'll have another equation here. You can go ahead and graph all of those on the same axes. Any questions on, I mean, you haven't really done these problems yet, but any questions on what I said so far about this problem? Okay, as you're working on it, if you get caught up on something, let me know, and then I can help you out with that while you're in your groups. I guess I'll continue through to the beginning of 3.1, since we're supposed to cover some of 3.1. Let's talk about quadratic functions now. So we want to be able to recognize when a given equation is a parabola or a quadratic function, which means that you have some kind of parabola on your hands. Parabola is the name for the type of curve that we get when we graph a quadratic function, right? So the function itself is called a quadratic function. So when you look at this is a quadratic function, and when we draw the graph, we're going to see some kind of U-shaped graph. That shape is called a parabola, right? So we don't call this a parabola, and we don't call the graph a quadratic shape. We call the equation a quadratic function, and then the graph itself is a parabola. We know the parent function, y equals x squared, or f of x equals x squared. We should kind of know how the shape of that one goes. So I'm going to draw y equals x squared with a dashed line, which would go through 0, 0, which would go through 1, 1, and negative 1, 1, and 2, 4, and negative 2, 4. So it'll go through those points. That is the parent function. Whoops. That's the parent function of the parent quadratic function, y equals x squared. And then if you guys remember our transformations section, we can talk about what each one of those things do to the parent function, right? So the square is coming from the parent function. Everything else, the negative outside the parenthesis, the -2 in the parenthesis, the +4 outside the parenthesis, those are going to do things to our graph to transform it. Which things are horizontal transformations on this given equation? So horizontally, what is a transformation on this equation?
The -2.
The -2, thank you. That's a horizontal transformation, which means which way do we shift the graph? Or which way does the -2 shift the graph?
The right.
Yes, we have a right to shift, right? And that's the only thing that's a horizontal transformation. The negative sign out front and the +4 are going to be vertical transformations. So vertical. What two things do we have happening vertically, and which one do we do first?
You flip it across the x-axis first.
Good. So reflect, or flip if you want to call it, reflect over x-axis. That's what the negative sign in front of the parentheses is going to do. And then what about the +4? What does that do?
Shifts it up.
And we're going to shift up 4. Good. So we're going to do that in that order. It doesn't matter if we do horizontal or vertical first, but within the vertical, we need to do it in this order. So let's do our new graph here, where we shift it right 2, we're going to shift all of the points right 2, and then we're going to reflect over the x-axis, and then we're going to shift up 4 units, right? So if I take a point, and I shift it to the right 2, like 0, 0, it ends up here. If I reflect over the x-axis, it doesn't go anywhere because it's at 0, because it's on the x-axis, and then I shift it up 4. This first point 0, 0 is going to end up here. And that's actually going to be my vertex. So if I label something here as the vertex, like the lowest point on the graph, then this will be my new vertex. All right, so that point shifted over to there. If I take this point at 1, 1 and I shift it right 2, it would be over here. And then if I reflect that over the x-axis, it would be here. And then if I shift up 4, it'll be at 3, right? So that point is going to end up here. And if we keep doing this with all of the points, we're going to get this parabola here. Right, it should be opening downwards because we did reflect over the x-axis at some point. And we shift it to the right and up 4, other than reflecting over the x-axis. Right, so we can use the old transformation definition that we have for these, like right 2, up 4, reflect over the x-axis. We can use that idea not just for graphing lines, but we can use that for quadratics as well. Determine the maximum value of this function. Remember, maximum value is going to be the highest point of a graph. So on the red line, what is the maximum value of this function? We'll write out the max. We'll just write out the point because it says to find the maximum point here. The maximum.
2,
yeah, so we'll write the maximum point as 2, 4. If the question was saying, I guess it does say determine the maximum value. Let's give 2 answers here because it's asking for 2 different things. The maximum point is going to be 2, 4, but the maximum value would always be asking for the y value of the highest point, which is 4. Right, the highest y value that we achieve is 4 here, but the maximum point, also known as the vertex of a parabola, is going to be 2, 4. Next part, part C says label the axis of symmetry, intercepts, and the vertex. As a quick reminder, when you have a parabola or a quadratic function drawn as a parabola, we have an axis of symmetry that runs right down through the middle of a parabola, goes through the vertex. It's called an axis of symmetry because the parabola is symmetric on both sides, kind of like a mirror image of itself. On both sides of that axis of symmetry. So when we do shifts and reflections and shift up and shift right, the axis of symmetry is essentially going to go with those transformations. Easiest way to find the axis of symmetry is just to draw a vertical line through the vertex. So if I were to draw a line through the vertex here, we would draw this vertical line that I'm drawing in green right now. And that we're going to label as the axis of symmetry. We'll say axis of symmetry, A of S. And we can actually write the equation of that line as a vertical line. Who can tell me the equation of that axis of symmetry?
Is x equals 2?
X equals 2. Good. Remember, a vertical line has an equation that's always x equals a number, and you determine the number by just looking at where it goes through the x-axis, right? So a vertical line, always x equals a number, but because it goes through 2, or every point on here, if you pick any point on here, it's 2 comma something, right? If I pick a point down here, that's 2 comma negative 3. That's 2 comma negative 5. That's 2 comma 0, 2 comma 1, 2 comma 2. X is always equal to 2, so the equation is x equals 2. So we've just labeled the axis of symmetry. That one is good. Label the intercepts. We're going to look for the intercepts here. The x-intercept here I'm seeing at 4 comma 0. I'm seeing an x-intercept. And then also at 0 comma 0 I'm seeing an x-intercept. So we'll label those two. What about the y-intercept? Where does my parabola, my red parabola, cross the y-axis? Where do we see the parabola crossing the y-axis?
At 0, 0.
Good, at 0, 0, which means we already labeled that one, so we don't need to label it again. So that 0, 0 will act as an x-intercept where it crosses the x-axis and where it crosses the y-axis, which makes sense because the x and y value are 0. So that's where the x and y-axis intersect each other. So if a line goes through that, then that is both an x-intercept and a y-intercept. And then finally the vertex. Let's label the vertex. I labeled it as vertex, but we should also write the point that the vertex is at. And we said that was the answer from part B, which is the maximum point of 2 comma 4. So that's our vertex labeled. Okay, so in general, when a question asks you whether or not you're using transformations, because we're going to see other ways of graphing parabolas, whether or not using transformations, whenever you graph a parabola on axes, you're going to want to label the axis of symmetry, which you draw as a dashed line going through the vertex. You want to label the x and y intercepts wherever it crosses the x-axis. Those are good points to have labeled on your graph. And then if there's a different place where it crosses the y-axis, you want to label that one as well. And then finally, labeling the vertex is pretty important because that tells you where that tells you where the axis of symmetry is. That tells you where the highest or lowest point is, depending on which way your parabola opens. It also tells you your maximum or minimum value in the y value of the vertex. Okay, so these three are going to be important to label on your graph whenever you do graph a quadratic function in the form of a parabola. We'll talk about this and then we'll stop there. So what do we know about, let me actually look at something really quickly. Give me one sec. Okay, we'll go over this page and the next one. So, understanding how the graph of a parabola is related to its quadratic function. So we have the standard form of a quadratic function given here, which is also called the vertex form. So if you hear vertex form or standard form, this is what we're looking at here. It's specifically called the vertex form because if you have a quadratic written in this form, then the vertex is at h comma k. So that's just right here. The h and the k automatically tell you where the vertex is. There is some kind of correlation between this being a horizontal shift and this is a vertical shift, right? And the parent function that we drew has a vertex at 0, 0. So when you include a horizontal shift of h and a vertical shift of k, that moves the vertex to a new position, right? So then h comma k is the vertex of the new parabola. So, but looking at this equation, you just look at what the number for h is and what the k is, and that gives you the vertex. And then a, the value of a, will tell you which way the parabola opens. So if a is a positive number, which means it's greater than 0, your parabola is going to open upward. And if your a is a negative value, then the parabola will be opening downwards. If a parabola opens upwards, it makes sense that the vertex is a minimum point, right? So that's not really saying anything revolutionary there. And if a parabola is opening downwards, like in the where a is negative, then the vertex is a maximum point because it's the highest point on the graph, right? So that last part is just kind of just stating the obvious. On whichever way the parabola opens, the vertex is going to be the minimum or maximum point. I think you guys can write the equation for that one. And then you can follow that one as well. I want to talk about the general form. The general form of a quadratic will be in its kind of multiplied out form, where it's not factored into the nice vertex form. Here, if we have a quadratic in this form, the general form, we can still find the vertex and the direction which it opens. We just have to do a little bit more work for the vertex. The vertex will be given by this formula. How we use this formula is we find negative b over 2a first, using the a and the b from the standard form. Then plug it into the equation. So we find negative b over 2a, and then we plug that into the original equation that we had to find the y component of the vertex. And we'll do more examples of this on Monday, so don't stress too much about this. I have a worksheet for us to work on today, which you don't need to do this for, but I'm trying to get to the factoring review so that we can do the factoring problems on the worksheet. And then the a in this equation is actually the same a as the other equation. So looking at this a, if a is positive, your parabola opens upwards. If a is negative, your parabola opens downwards. So that's the same for both forms. And in fact, that a is actually the same a that you have in the other form as well. So the numbers will be the exact same if you go from one form to the other. So let's review factoring. You guys should have some kind of background on how to factor. So I'm going to explain this, but it should ring some bells as I'm explaining this. The first thing we look for when we're factoring is a greatest common factor. Where do I want to put that? So first, look for a greatest common factor. Actually, in the chat, everyone that's here, can you give me a number 1 through 5 on how comfortable you are with factoring something like this, where you have a trinomial and you're asked to factor. First, you look for any common factors, and then you use either the X method or the box method or whatever method you learned to factor this into like the two parentheses. So give me a number 1 through 5 in the chat on how comfortable you are factoring using an X method or a box method. Those are actually decent numbers. 3 and 4 are good, better than average. So I'm gonna let you guys work on the worksheets, and then I'll come around to the rooms. So I'm gonna stop there.